A very good morning, ma. And today's class we will be learning about the electromagnetic induction, a new chapter, electromagnetic induction, or simply we can call it as EMI, electromagnetic induction, EMI. So what this chapter is going to deal, that is what we need to discuss. First we will go with the introduction of this chapter. As I told you in moving charges and magnetism, so electricity is not a different topic and magnetism is not a different topic. They are put together. We will be learning it as an electromagnetism, yes or no. In olden days, some around 2000 years before, we'll be learning electricity separately and magnetism separately. But now in the present situation, we are we have understood that electricity and magnetism are not separable. They are just like the two faces of a coin, and that is called as electromagnetic induction. The basis for this electromagnetic induction was based on the ideas of Faradays Ampere. Faraday, Ampere and Henry. Some other scientists are responsible for the development of this electromagnetic induction. So what this electromagnetic induction says, if you won't study about electromagnetic induction, what is going to happen? So in this electromagnetic induction, what we are understanding means, we are first understanding about the Faraday's laws of induction, Lenz's law and motional EMF. So why to learn all these things means, so in the beginning of the 19th centuries, in the beginning of 19th century, in the first decades of the 19th century or else, Michael Faraday has noticed some facts. What is the fact he noticed means, when there is a relative motion between a coil and a bar magnet, an induced current is developed. Why an induced current is developed is the question raised in his mind. And he has told that a phenomenon discovered by him for the fellow scientist, and the fellow scientist has questioned him, what is the use of your new observed phenomenon? So he has told that when there is a relative motion between the coil and the magnet, there is an induced current. Then this was revealed for his friends and or the fellow scientists, and he told about his discovery. But when he has told about his discovery, the immediate question came for him is what is the use of your newly observed phenomenon? Then he has answered him like this: what is the use of a newly born baby? Can you say what is the use of a newly born baby? When PM Modi was born, and does anybody knows that he will become the Prime Minister of India? So we don't know. Among you also, I can't say what you are going to be in the next coming decades. So at present I cannot say what a newly born baby is going to be, because he may become a scientist, he may become a chief minister, or he may become something else. So we cannot say what is the advantage of that at the beginning stages. When you understood this phenomenon, let us try for the advantages, applications of this phenomenon. That is what told by Michael Faraday. And he has made two important laws called Faraday's first law of induction and Faraday's second law of induction. In this chapter, or the entire chapter is especially based on the Faraday's laws of induction. If we have not followed the Faraday's laws of induction, right now we might be in the darkness only, because nowadays we are having electricity. Because of what? We are having the power plants. What kind of power plants we are having? We are having hydrothermal power plants are there, nuclear power plants are there, thermal power plants are there, like this, so many power plants are there. But for all these power plants, a generator is required. The generator is working based on the Faraday's laws of induction only. Okay, if Faraday's laws of induction were not understood, right now we might be in a different situation. Just think of the world without the electrical power. So we are generating the electrical power based on the generators, and whose basic ideas are formulated on the Faraday's laws of induction. So it is important to learn about this electromagnetic induction chapter. So what we know, in the beginning electricity was dealt as a different topic and magnetism was dealt as a different topic. In the year 1820, after Oersted's observation that when a current is passing through a wire, a magnetic field is produced. This is what Oersted has discovered. Later, we came to know that if because of the current or because of the moving charges, there is a magnetic field means, the immediate question came to their mind means, if magnetic field is varied, can you have the current? And the sounding answer for that is yes, because nature is a subject, physics is a subject of symmetry, or nature loves symmetry. We are discussing about the nature means we are discussing about the physics. So, study of laws of nature is nothing but physics. Now, if moving charges are producing the magnetic field, then why can't a moving magnet can produce the electric current? This is the question, and the sounding answer for that question is yes, even from the moving magnets we are able to produce the electric current. That is what we are going to study in this Faraday's laws of induction. Then in this Faraday's laws of induction, first we will discuss about the Faraday's first law of induction, and then we will go with the Faraday's second law of induction. For that, the Faraday's first law of induction is not just based on the simple one or two experiments. A series of experiments were carried out by Faraday, Michael Faraday and Henry. Both of them are belonging to the different countries. Henry belonged to the USA and Faraday belonged to Germany. And these two fellows carried out a series of experiments, and from those experiments they came to a conclusion. Their conclusions were kept in two laws. One is called Faraday's first law of induction, and second one is Faraday's second law of induction. So first we will discuss about some of the experiments that are carried out by Faraday, Michael Faraday. So what he did we will see here. He has taken a coil. First he has taken a coil. This is a coil. And this coil is connected to a galvanometer. What is a galvanometer? A galvanometer is a current sensitive device, and it is used to measure very small currents of the order of microampere or 10 power minus 6 ampere. Even a small current passes through this coil also, we can see the deflection in the galvanometer. The deflection in the galvanometer says that there is a current in the coil. If there is no deflection, there is no current. But if there is a deflection, there must be a current. Now first tell me, can you expect any current in the galvanometer? Or can you expect the flow of current in this coil? This is a coil. Can you expect any current? The answer is yes or no. The answer will be no. Why? Because for a current to be there, what must be required? In current electricity we have studied. A current will pass through the conducting rod, provided the two ends of the rod are connected to a battery. So what the battery is doing, suppose this is a conducting wire. Having a conducting wire, I can't have the current because there is some requirement. What is that requirement? If the current to be flown through this wire AB from A to B, then A must be at higher potential and B must be at lower potential. And who is providing this potential difference between A and B? A battery. So if I purchased a battery from the shop, having a battery, we can't have the current. That battery must be connected to the two ends of the conductor. If the two ends are connected like this battery is developing the potential difference between the points A and B. Because of this potential difference developed by the battery or the source of electrical power, a current is flowing from A to B. That is the requirement for current. So there must be what between these 2 points A and B? There must be some voltage difference or potential difference, or there must be some EMF between the points A and B. So that EMF is generated by whom here? Battery, while what we study in the current electricity part. If you see this case, there is a conducting path. A wire is a coil is made up of copper only, and it is a conducting wire only. So conducting wire is there, and that too it is closed also. That too it is closed. Though it is closed and it is conducting, we can't expect any current. Why? Because there is no source of current here. That means a battery is not there. A physical battery you can't see here. Yes sir. So our expectation is there should not be any current in the coil. But now what Faraday did we will see here. He has taken a bar magnet now. He has taken a bar magnet like this. And this bar magnet is consisting of north and south poles like this. Now this bar magnet is kept along the axial line. Now this bar magnet is moved like this. When the bar magnet with this being the north and with this being the south, if the bar magnet is moved like this, what is happening? Around the magnet we know that there is a magnetic field. When you bring the magnet close to the coil, what is happening? The magnetic lines of this bar magnet are linking with the coil, and that linked magnetic field, is it constant? No. When it is brought nearer, the flux linked with the coil is changing. It is increasing or decreasing. When it comes like this, the lines are increasing like this. Magnetic lines will be increased in this way. So there is a change in magnetic flux linked with the coil. Now when the bar magnet is brought closer, he has noticed that there is a deflection in the galvanometer coil. So there is a deflection means how the deflection is there means what? There is a current in the coil. There is a current means there must be what? Without an EMF we can't expect the current. That means there must be an EMF. And who is providing that EMF is the question here. So we have seen the current. Current is there means there must be a potential drop or potential difference should be there. There is no physical battery here, but we are observing a deflection in the galvanometer. That means when a bar magnet is brought closer to the coil, you are noticing a current means when the bar magnet is brought nearer to the coil, an EMF is generated. And that EMF generated is called as induced EMF. And he also noticed that, and now when this is brought like this, what is happening means flux is increasing in this way. And now the current will be in this way. I will tell you why we are getting the direction like this later. So in the coil, the current is coming in this way. Why it comes like this only? Why it won't be in anti-clockwise direction? I will tell you later after the discussion of the Lenz's law. Okay. What we have to notice is in the experiment number 1, our Faraday, what he did means he has chosen a coil, and that coil is connected to a galvanometer, and a bar magnet is kept along the axis of this coil, and this bar magnet is brought closer to the coil. Then flux linked with the coil is changing, and he noticed a deflection in the galvanometer. He noticed a deflection in the galvanometer. When he moved the magnet away, then he noticed an opposite kind of deflection. Instead of moving the magnet closer, he moved the magnet away. Then he noticed an opposite kind of deflection. Similarly, by interchanging north and south poles also, once he brought the magnet closer and the other time he moved the magnet away. In such case also, we have some opposite deflections. That means when the south pole is brought closer, you will be having a deflection on one direction. When you are moving it away, you are getting an opposite deflection. In the second time, what he did means, he fixed the magnet. Now he moved the coil. First case, what he did, he fixed the coil and moved the magnet closer and farther, once by keeping the north pole this side, and the other time keeping the south pole like this, he moved the magnet closer and farther. So in these cases, he noticed the deflection. Deflection there means there is a current. Current there means there must be an EMF. Without EMF, we never have the current. Okay. So an induced EMF is developed. That is the first thing that we can conclude using this experiment. So in this experiment, once he kept the coil fixed and the bar magnet is moved. Second time, he fixed the bar magnet and moved the coil here and there, closer and farther away from the magnet. In all these cases, he noticed deflection in the coil. That means whether the coil is moving or the magnet is moving, or else whenever there is a relative motion, relative motion between coil and magnet, there is a induced EMF and there is a current. That current is called as induced current. The current that is generated because of the induced EMF is called as induced current. This is experiment number 1. In experiment number 2, what he did. So in the second case, he has not used the bar magnet. Instead of using the bar magnet, he used a coil. So he used a coil. This coil is as it is. First coil will be kept as it is with a galvanometer like this. In the beginning, we never expect any current to it. And secondly, he has chosen another coil like this, and this coil is connected to a battery like this. Now what is going to happen? When a current is passing through this, you can expect the current passage. Yes or no? And this is nothing but what? Solenoid. And a solenoid means what? A bar magnet. In previous chapter we studied that solenoid will behave like a bar magnet. That means I am replacing the bar magnet with an equivalent of it. The equivalent of bar magnet is nothing but what? A solenoid. A solenoid is taken, that means this coil 2 is behaving like the bar magnet. This is coil 1 and this is coil 2, and their axes are common, they are coaxial. Now what he did is, in this case he moved the magnet closer and farther. In a similar way he moved this coil 2 or C2 coil is brought closer and then moved farther. When the solenoid is brought closer, he noticed a deflection on one side, and when it is moved away he noticed a deflection opposite side. In the similar way, he fixed C2 coil and moved C1 closer and farther. He noticed the opposite kind of deflection. That means here what is there? Between the two coils, again there is a relative motion. So whenever there is a relative motion between the coil and the magnet, you are expecting the current called as induced current, and the EMF is said to be induced EMF. In second case what he did, he has replaced the bar magnet with another coil, which is nothing but a solenoid. Solenoid will behave like a bar magnet. Here also he repeated the same story what he did with the bar magnet. So he moved the coil C2 closer to the coil C1. He noticed one side deflection. When he moved it away, he noticed the opposite kind of deflection. Secondly, he fixed the coil C2 and moved the coil C1 closer and farther. Again he noticed the deflection. When both the coils are not moving, then will you have any current? You won't have any kind of current because you never notice any deflection. Here also, when the bar magnet is fixed and the coil is also fixed, then there is no relative motion between them and the current in the coil will be 0, which says that these two experiments will say that whenever there is a relative motion between the bar magnet and the coil or between the two coils, then there is an induced EMF, and which will be responsible for induced current. Is it clear or not? So here, because of this one, the current is passing like this and it is going like this. So magnetic field is like this. So magnetic field is like this, and it is increasing one, therefore it should be opposite direction like this. Okay, now. So these are the two experiments, and one more experiment we have to discuss, which will give the clear picture about this electromagnetic induction. Okay, what is that experiment means? The second coil is connected with a plug key like this. With a battery and plug key it is connected. Now what he did means, he has not moved the coil C1 nor the coil C2. Both the coils are not moved. C1 is fixed, even C2 is also fixed, but their axes are coaxial. What he did? He closed the plug key. When he closed the plug key, current in the solenoid will increase. Current is set up in the solenoid. Does the current is set up immediately? No. The current will increase in the solenoid from 0 to a maximum, and the time order will be of the order of microseconds. Even though the time gap is very small, but current is increasing from 0 to a maximum value in a momentary time. Just like when I switch on the switch here, the fan will immediately start. We may think that it is an instantaneous phenomenon, but when you switch on and the fan is running, there will be some time gap. That time gap is negligible for us. So, but in physics, even that time gap is also considerable. Here, when I close the plug key, the current is not immediately becoming maximum. There will be some time gap which is of the order of microseconds or more. So when you close the plug key here, then current is set up in this one, which increases from 0 to a maximum value. Because of that one, when current changes in the coil, magnetic field also changes. When that magnetic field is changing, that magnetic field linked with C2 coil is also linked with the coil C1. Then what you notice means, on closing this plug key, you are having a momentarily deflection. If it is closed, you will have a deflection, and again it comes back. So only for a moment only we can notice a deflection. Just it will show deflection like this and comes back. Again, when I break the circuit, when I make the circuit, you had a deflection. When I break the circuit, again we had a deflection opposite direction. So when you are making the circuit and breaking the circuit, you are having the deflection in the coil. So, in this case, do you have any relative motion between C1 and C2? No, there is no relative motion between C1 and C2 because both of them are fixed. But when this is closed and open, you are noticing deflection means what is happening while you are closing the plug key and when you are opening the plug key. When you are closing the plug key, current is increasing from 0 to a maximum while making the circuit. While making circuit, current increases from 0 to maximum and maximum to 0 while breaking circuit. Breaking circuit. So, when the current in this is changes, then the magnetic field mu naught Ni linked with this coil is also changes. The magnetic field linked with this is also be linked with this one. So, then that magnetic field is not a steady magnetic field, but it is a variable magnetic field. So, whenever the magnetic field linked with the coils is varying, then only we are noticing the deflection. So, finally, what is the main reason for electric current here? Is it the relative motion between the coil and the magnet, or between a coil and another coil, or the change in magnetic flux linked with the coil, which is the reason for the magnetic induction here? It is not the relative motion, because though from first and second experiment we notice that relative motion is there means there is a deflection. But in this case, even though there is no relative motion, we are having the induced current, which says that relative motion is not the basic criteria for electromagnetic induction. Please remember, relative motion is not the main reason for electromagnetic induction. Then what is the main reason means? The changing magnetic flux linked with the coil is the main reason. See here, in this case, when this is brought closure, what is happening? Flux linked with this coil is also linked with this one. When this is brought closure, flux linked with this also increases. When it is moved away, flux linked with this coil is decreasing. So, when you are moving the coil or bar magnet, then what is happening means flux linked with the coil C1 is changing. This changing magnetic flux is responsible for the induced EMF and the induced current, but not the relative motion. Due to relative motion, we are getting the change in magnetic flux. What is happening because of relative motion? Due to relative motion, we are having a change in magnetic flux, and that change in magnetic flux linked with the coil is responsible for the induced EMF and the induced current. So, final conclusion of these three experiments are: first thing, relative motion is not the reason for electromagnetic induction. Second point, due to relative motion, there will be a change in magnetic flux linked with the coils. And third one, the final utmost important one is the change in magnetic flux linked with the coil is responsible for electromagnetic induction. And one more thing is, when he moved this coil much faster, then he noticed the more amount of deflection. When he moved it slower, he noticed a small amount of deflection. That means how fast he is moving the bar magnet or the coil is deciding the amount of induced current developed. Is it clear or not? That means the rate of change of flux, is responsible for calculating the amount of induced current. That we will discuss in the second law, that is Faraday's second law of induction. So, now I will write the Faraday's first law of induction statement and Faraday's second law of induction statement, which will be very important for understanding this subject as well as for board examination. In the 1 and 2 mark questions, they will ask you to write the statements for Faraday's first law of induction, Faraday's second law of induction. Now, coming to the first law of induction, what the first law of induction says: whenever there is a change in magnetic flux linked with the coil changes, then there is an induced EMF, and if the coil is a closed coil, then there will be an induced current also. Faraday's first law of induction. Faraday's first law of induction. So, what it says? Whenever there is a change in magnetic flux, this is important, change in magnetic flux linked with the coil, then there is an induced EMF. There is an induced EMF. If the coil is closed coil, along with this induced EMF, there is also an induced current. What is Faraday's first law of induction says? Whenever there is a change in magnetic flux linked with the coil, then there is an induced EMF with that coil. If the coil is closed coil, along with that induced EMF, then there is an induced current. So, induced EMF will be there whether the coil is closed coil or open coil. In both the cases, induced EMF will be there. But induced current will be there only in the closed coil. There won't be induced current in this case. Though induced EMF is there, the induced current won't be there if the circuit is open. If it is closed, induced EMF will be there, along with that induced current is also there. It is just like the case you have purchased a battery from the shop. You brought it home. Will you have current? No. Battery there doesn't mean that there must be a current. When the battery is connected to a bulb, then only bulb will glow. Battery having, bulb having, simply keeping like this, no current will flow. Yes or no? Open circuits, there won't be any current flow. Closed circuit, there will be a current flow. Here it is the case of battery which is not connected to anything. And here it is the case where battery is connected to the closed loop. Is it clear? Now, so when the flux linked with the coils changes, then there is an induced EMF. If the coil is closed, then there will be also an induced current. Now, the second question immediately what we will have is, induced EMF is there, okay, but how much? You are saying that induced EMF is there, but how much induced EMF is there is the question. The amount of induced EMF will be decided by the Faraday's second law of induction. So, the amount of induced EMF, first law says that an induced EMF will be developed when flux is changing with the coil. Second law says that how much EMF is developed. Faraday's second law. So, first I will write the mathematical formula so that you can understand it better way. The amount of induced EMF is equal to minus d by dt of phi. In previous classes, I already told you what is meant by phi. Phi stands for what? Flux. Which flux here? Magnetic flux. Phi stands for magnetic flux. You know how to read d by dt. D by dt is read as rate of change. Yes or no? So, what is d by dt of phi? Rate of change of flux. Which flux? Magnetic flux. Rate of change of magnetic flux. Here E stands for induced EMF. Induced EMF is equal to, what is this? Negative. So, induced EMF is equal to negative rate of change of magnetic flux. The amount of induced EMF, what Faraday's second law says? The amount of induced EMF, the amount of induced EMF E is equal to, just see this formula we can write on our own. The amount of induced EMF is equal to negative rate of change of magnetic flux linked with the coil. Negative rate of change of magnetic flux linked with the coil. That is, you can write the formula like this. Is it clear or not? So, instead of remembering the statement, better you remember the formula. From the formula, we can construct the definition. Formula, if you remember formula, we will be getting the formula, and on our own, we can frame the statement. So, better remember that E is equal to minus d phi by dt, where E stands for EMF, phi stands for magnetic flux. So, first law says, whenever the flux linked with the coil changes, then there is an induced EMF. Second law says, how much EMF is induced? The amount of induced EMF is equal to negative rate of change of magnetic flux linked with the coil. Why the negative sign is introduced here? Negative sign is introduced in accordance with the Lenz's law. Negative sign is in accordance with Lenz's law. I will tell you what is this Lenz's law next. So, just remember here I have introduced the negative sign, and that negative sign is in accordance with which law? Lenz's law. Is it clear? So, this is about the Faraday's first law of induction and Faraday's second law of induction, and next we will discuss about the Lenz's law. Is it clear?